What's happening, folks? Geologist Philip Prince talking about volcanoes and oil and gas today. Kind of an interesting combination, but at least in this video, they're going to be occurring in pretty different parts of the Earth's crust. Had a viewer question, why is there not a ring of fire in the Atlantic Ocean? So over here on the right side of the screen, um, big ocean, continents come up next to it. You don't see volcanoes and you don't see a lot of big earthquake activity in this location. Over here on the west side of South America, plenty of volcanic activity, plenty of big earthquakes, and you can follow that very active zone all the way around the edge of the Pacific, Aleutian Islands, Alaska, all the way over here, Kamchatka, down past Japan, Mariana Islands, and it keeps going, right? So pretty much everywhere around the edge of the Pacific, you got volcanoes and earthquakes. Over here in the Atlantic, you don't see that, but you see quite a bit of oil and gas exploration, and a lot of that leads to oil and gas production. So what's the difference here? Pretty cool question to answer. Pretty cool question to try to diagram, because the sketches that you have to come up with here are sort of iconic within the study of geology and plate tectonics. So it's fun to put them together. We'll start off here on the volcano side of things. Why is there a ring of fire? You look here in southern part of the Andes in Chile, you will see occasionally you got these isolated little white pointy mountains. Zoom in on one of them, really cool, like classic looking volcanoes. Sort of a cone-shaped mountain, often with a little bit of a crater in the middle of it, and here all this stuff that's erupted out of it. So always neat to look at those on Google Earth. Why are they there? It's all about what's under the edge of the South American continent here, and what's under it is this oceanic plate that is sinking or subducting under the edge of the continent, right? So what you got here on the ocean bottom, it's actually going down underneath South America, and that induces melting in the Earth's mantle, and that comes up and erupts at the surface. So what would that look like? True classic here. We'll see how well we can do with it. Going to be our volcano. All right. Got to keep these lines closed so we can color this one in. So there's our sinking oceanic crust. So this is the plate that's down underneath the Pacific Ocean. Got kind of a thick spot in the overriding plate, which is going to be the South American plate. That's going to be like continental crust. We're actually going to color these differently because they are different rock types. Underneath it, though, we're going to make all the rocks of the mantle green, because if you could see mantle rock at the surface, it would be green. And down here deep, 60 plus miles, 100 kilometers or more deep, as this oceanic plate sinks down, there's a little bit of water mixed into the minerals among other chemical compounds, and they start to sort of sweat out of that, if you want to call it that. And that causes melting in the rocks of the mantle above it, and that's the material that actually comes out and erupts to produce the volcanoes in that part of South America, and elsewhere in the ring of fire. Can I fill in that spot? Oh yes, got it. Okay. So let's turn this into kind of a full block diagram here, and we can even get some ocean bottom mixed into it as well. Okay, so this is gonna do the ocean here, have our deep spot, ourselves kind of a coastline there. Looking good. Color in the landscape, do the ocean water now. Nice. Okay. Add a little bit of detail under the ocean here. You do get this deep trench where that sinking or subducting plate is kind of bending. It's like bending to go down underneath the overriding plate. And we'll give ourselves a little bit of terrain detail up here on the land surface as well. Get pretty big mountains here. The continental crust is thicker. It's always going to give you higher elevations. And in this particular case, because the plates are coming together, there's going to be thrust faulting involved. It's going to be stacking big sheets or sort of slabs of the crust there on top of each other to thicken it up and support those bigger mountains. And we'll have some more of that going on out here as well. Okay, there's going to be volcano. We'll give one more out here. And give it that cone shape there. Even maybe give it a little bit of a snow cap. Cool. So pretty basic ring of fire setup there. And volcanoes like this in a setting like this have the potential to make pretty big explosive eruptions. And that's because the material that's erupting out of them is actually the result of melting above that sinking slab. So it all comes down to what's going on down here with that water and other chemical compounds sort of sweating out of that sinking plate. How did the water get into those minerals? That plate actually erupted at a mid-ocean ridge to make ocean floor, and it sat around underneath the ocean for quite some time. So the sinking oceanic crust there, it actually has water in it. It's not water that you can wring out like a sponge, but when you get it down there deep, it heats up and that water starts to come out of it. Now, does the sinking plate itself melt? No, it can't heat up fast enough. Rock conducts heat really slowly, so it can't get hot enough to melt itself, but it can get hot enough for the minerals that have water to break down. And that's what gets that melting process going and gives you those big eruptions and those volcanic mountains. Now we can tailor this diagram here just a little bit to show what you might see in like an ocean island out in the Pacific, because not all of the Pacific Ring of Fire is some kind of like a big mountain range on the edge of a continent. Quite a bit of it is just isolated islands sort of sitting out in the middle of the ocean. And in the case of those islands, it's the same type of a concept. You got the sinking plate going on. It's just the overriding plate is not that thick continental plate. It's more oceanic crust. So we should be able to kind of tailor up our drawing here pretty quickly and turn it into something that would be more representative of what you might in one of those ocean island settings. So we need to kind of expand our ocean here just a little bit. There we go. So there's going to be our volcanic island and get pretty deep again on either side of that. See how we do with that here. Probably good enough. Okay, let's fill in more ocean up there. I don't need that color. Ooh, cool. All right. So let's tidy up that last little bit of leftover land there. So in this case, we're going to have a few of these little islands. Good for them to have friends there. I think people that like the Bob Ross comparison, they might enjoy that. But there's our ocean islands, and they're going to have volcanoes that may or may not be erupting, but will have had eruptive history. And in fact, the islands themselves are islands because enough material has erupted there to cause them to rise out of the water. There's also quite a bit of heat, of course, associated with this molten rock rising. So add that. Let's see if we can give ourselves just a little bit underneath that. There we go. Looking good. Okay. So there's your sort of basic ocean island in the Ring of Fire set up right there. Fill it in. You get deeper ocean trenches in situations like this just because of the nature of the plates that are coming together. But the scene you're seeing right there, um, you could go onto Google Earth, take yourself out into the Western Pacific, which we will do right now, and really look for any of these dark lines. Those are those dark trench areas, and those are going to tell you where the plate is sinking and that's going to tell you where you might see that volcanic activity, and you get a lot of earthquake activity with that as well because of the sinking plate. So we'll zoom in. We'll pick this dark trench right here. Let's zoom in there and see what we see here. Okay, pick an island. Let's just see what they look like. See if we can find a volcano on one of these. Yes, there we go. Look good. So you can just kind of expect to see this because this is how geology works, and you'll end up with this really cool, like classic tropical looking island volcano. Might even have some steam and smoke coming out of it there. Who knows what kind of awful sulfur gases those might be. But this one has a pretty recent eruptive history, nice crater on it there. Everything you'd expect, use it in a movie set or something like that. And it, of course, is sitting right where you would expect it to be in the ring of fire there. All right, so that's kind of the ring of fire thing. And when you see that scene, that's kind of your visual sinking plate causing melting in the rocks of the mantle above it. That's what erupts out. All right, so we got fire squared away here. Okay, so now what's up in the Atlantic? Actually, kind of the kind of the main idea of the video, but you need to have a basis for comparison there. So say we took the other side of South America here. You could do this for the east coast of the US, West Africa, whatever you like. You don't have that deep ocean trench, you don't have the mountains, you don't have the volcanoes. Really there's just shallow water for a ways, shallow water, and then it gets deeper. Sometimes there's a little bit of topography, but a lot of times the land is quite flat before it goes offshore. So what's the deal down there? Now this is a drawing that escalates quickly, and it's actually going to lead into a whole nother video. Doing the land surface here is pretty easy because there isn't really much of one to draw, just because it's pretty much flat and very almost imperceptibly sloped down to sea level. It's what's going on in a later phase of the drawing that really gets serious. So in this particular case, what's under the edge of that continent is a really stretched and thinned out zone of continental crust. Obviously, there's not a closed line there. Right now, yes. And that transitions out into that same oceanic crust that we drew sinking in the previous sketch there. Nothing is sinking here. Nothing is going down into the mantle in this particular sketch. There's no mantle rock that's rising up quickly. That's another way to produce volcanic activity in the Earth system. Everything's just kind of sitting here, and in particular, uh, this kind of like thinned out continental crust. If you saw it diagrammed, it would have this kind of like broken appearance like that. It was like it is broken almost into little steps. And each of those actually sort of separates little individual sedimentary basins that we'll color in brown here. And these are related to stretching and breaking apart the supercontinent Pangea in this case. So when you stretch Earth's crust, it kind of cracks, if you will, as it stretches, and it produces those basins that fill in the sediment. And then you could fill in a whole heck of a lot more sediment on top of those. So there's that really shallow water, and we're going to let that get deeper as we make our way offshore. So let's see if we can get our lines looking good there. I don't like that one either. This better do it or I quit. That'll work right there. Okay. So on top of those deep sediments, there's just a whole lot more sediment. In fact, when you look at the edge of a continent like this, we'll kind of tilt the view like this. What you're seeing there, it's almost this kind of spoon-shaped thing that is tailor-made to collect huge amounts of sediment that are eroding off of that continent. And I don't know, I still don't like my sediment profile there because we're actually going to have to throw quite a few details into this one. And indeed, what goes on in these accumulations of sediment, like I've just sketched in here, particularly this thicker upper one, this receives about as much geologic study as anything on the planet because that's where quite a few oil and gas resources tend to occur. Right. So we'll finish out the diagram here with some ocean bottom there. Get everything filled in. Nice. Okay. Need a little bit of deeper water. This is going to be kind of our step down there towards the deeper ocean. All right, cool. So this particular case, there's nothing going down in the mantle. The mantle's not rising up while it's still hot to lower pressure shallower in the earth. There's nothing to drive any kind of melting that's going to erupt and produce volcanoes. This continental margin, it just kind of sits here, and it's actually called a passive margin for that reason. The tectonic activity in the Atlantic, it's all going on out here in the mid-ocean ridge, which is being pulled apart. Okay, so this passive margin is just along for the ride, and it has been doing a very nice job of collecting huge amounts of sediment. How much is huge? Miles or kilometers. A lot of places you might go as high as pushing 10 kilometers, and that would be from ocean bottom down like to the bottom of one of those basins, right? Some places you go well beyond that. In the Gulf of Mexico, sort of right where the Mississippi and its ancestor rivers have been depositing sediment for quite a while. Believe it or not, the sediment fill there is up to 60,000 feet thick. So 12 or so miles, about 20 kilometers. That's pretty thick, but that's a result of focused depositing of sediment on this wheat crust here. The more you pour onto that, kind of the deeper it sinks and sags down under the weight. Most places, of course, around the Atlantic, they ain't gonna be that thick, but that's the name of the game. This is a place that collects huge thicknesses of sediment, and once enough of that material piles up, it starts to do something pretty interesting. The reason I've drawn that line on there is we're actually going to have to try to show some of the structures that are going to develop in a place like this. There's not any kind of tectonic collision or here or whatever, but under the weight of the sediment and the fact that it does kind of have that faint slope, it actually tends to kind of slide out there towards the deeper ocean basin. And this is where it gets really serious. So what you might see, this is in the simplest way possible. I'm going to do another video where I kind of get deeper into this. We're going to bend that way. We'll bend it that way there. See, we'll do one more of them. Okay. So as the sediment slides there, it kind of stacks up and folds on top of itself out to sea, and you get these sort of breakaway structures where it pulls away and kind of drops sequences of the sediment downward, and that makes more space for more material to fill in. So you have areas here that are being stretched apart, and then you have areas that are being crunched down there at the toe toward the ocean basin. We'll tidy up a few of the details here, and should end up with a halfway decent. And again, this is highly simplified. We're just trying to kind of show the basic concepts here, and we'll actually give those a little bit of an expression on the seafloor down there. Okay, cool. Looking good. All right. So any sticklers watching, I'm trying to Trying to do a decent job there. Okay, cool. So there's structures within our huge, enormous sequence of sediment that's filled up the edge of the continent here. And if you're looking for oil and gas here, you're going to be interested in these structures. We'll make our wells in red. Go down, check that out, check that out. We can do one really far, way offshore. It looks like our sea surface has a bend in it there. That's just bad. That's bad drawing. So go down and check that thing out. All right, so these offshore exploration enterprises are looking at some of these areas where the layering has been disturbed, and that is allowing the rising oil and gas to kind of go up there and get trapped in these structures, and that's what people are targeting there, right? So the two types of continental margins are totally different in terms of what's actually going on, sort of all the way down there in Earth's mantle. And in this particular case, what we're drawing here in the geologic future, yes, this process will this process will begin, and there will be melt generation and whatever else in the geologic future, well down the road. We're not there yet, and this overall appearance that you see here is a decent way of thinking about what's underneath pretty much all of eastern South America there. Can take it all the way up and do Gulf of Mexico, eastern North America, maritime Canada. There's oil and gas production here. And if we go over to the other side of the Atlantic, it's kind of the same idea. We would just flip our image around like that, and you're essentially looking at the main idea along West Africa. If you Google any country in West Africa that has a coastline and put oil and gas with it, someone has thought about it. And again, it's going to be in these shallow areas out towards this sort of like drop off where things are dropping off to the deep water, right? So why is the entire Atlantic Basin surrounded by this potential? Well, it looks like South America might fit into Africa there. Correct. We are not the first to think of this. This is Pangea pulling apart. So this is the breakup of the supercontinent. These passive margins that collect all the sediment form after that breakup has sort of completed and the continents are just drifting apart. What's the flip side of that coin? If you have a supercontinent, you have to have a super ocean. It was called the Panthalastic Ocean. The Pacific is kind of the remnant of that. And so as the supercontinent breaks apart, those moving continents have to they have to go somewhere, and they go somewhere by consuming the oceanic crust that was underneath the Panthalastic Ocean. So the Pacific is kind of the leftover of this super ocean, and as those plates sink, the Pacific is being consumed, as the Atlantic kind of grows with the spreading there. So two different types of continental margins, two different geologic structures. But to get that fire element mixed into things, something has to be either introduced to Earth's mantle, or Earth's mantle has to be able to rise upward pretty quickly. And you don't have that going on a passive margin, right? All you have going on a passive margin is a lot of sediment accumulation. And when those sediments pile up thick enough down here deep in this miles, kilometers thick accumulation, that's where you generate oil and gas, and that migrates upward and gets stuck in places in the sediment fill that you can drill in and get it. So kind of a cool way of looking at the Earth. I thought it was an awesome question, because it's like, there's sort of a ring bordering the Atlantic. So what makes it any different from the Pacific? Here's your answer. So I hope you enjoyed this video. Hope you check out the next one when it comes out.